Hi, this is Jamin Bowen from Xilinx. I'm very excited to join this delayed remote presentation on the new era of software-defined networking and storage infrastructure and what Xilinx is doing to address this changing landscape. So there's really three big trends that are taking place that are impacting how infrastructure is being deployed throughout our industry. The first one, and I'm sure you've heard this before, is that compute is changing. Basically, frequencies have hit a brick wall where we used to be able to deal with a higher and higher frequency just bringing performance to the table. We can no longer count on that anymore. Really, you have to think about doing compute a little bit differently. The second impact is the cost per unit of yielded area is going up from the silicon perspective, where for each die you can get more transistors, but the cost to do that is just increasing. So what this really means put together is that compute architectures need to evolve to keep delivering performance. New architectures are delivered by having a hardware acceleration with a software programmable infrastructure. The second big trend is in networking. Port speeds keep increasing versus compute. And it's really interesting to just look at this across recent history. And so as data continues to grow and go forward, there's a need to share it, to have computers work together. And this just has driven an unrelenting increase in the amount of network performance that's required. And so when we look at this over the last 10 years with a little bit of projection, we can see that the network port speed per server is vastly outpacing the compute cycles per server in terms of compute horsepower per socket. And that is leading to new infrastructure, new requirements, and new network loads that just didn't happen in the past. The last trend is this explosion of data. Basically, video, the Internet of Things are driving an explosion in data that's being created, captured, analyzed. Flash storage at the same time is lowering the latency and increasing the bandwidth, so your ability to analyze this data is unlocked like it never has been before. But moving this data back and forth between the CPU and storage creates bottlenecks and it consumes power. And there's nothing that makes it look like this continual rush of data is going to slow down anytime soon. So with that, I'd like to go over just what are these bottlenecks in infrastructure and what can be done about them. First, let's take a look at network processing bottlenecks. What we're looking at here is a typical virtualized server environment. A large number of VMs are sharing the same physical infrastructure. And a big part of the network processing workload is ensuring that the packets that are intended for a particular VM make it to it directly. In a traditional server architecture, this involves a shared conventional NIC, receiving a packet, transferring it up to the shared host CPU, and having the hypervisor perform the packet processing, the virtual switch lookups, the tunneling, and in many cases some security workload as well. This results in excessive CPU utilization. This is work that is not available for VMs, and it's also high latency, and ultimately it limits the data rates. And it's not scalable as the network speeds grow. Eventually, you'd get to the point where the entire CPU would be used purely for this packet processing, and there wouldn't be any left over for the actual workload that's being done within the VMs. So what's the solution? It's moving the processing to optimized hardware. So rather than having packet processing take place on the host CPU, it can be moved out into the NIC, in this case implemented on an FPGA. And now as packets come in, this packet processing can be done directly. The virtual switch lookup table can be handled within the NIC. The actual tunneling and so on and security can take place before any packet even goes on to the host VM. This improves the CPU utilization for more generic workloads. It enables a much higher data plane performance, and ultimately it scales to keep up with network speeds as they continue to increase. Now let's turn our attention to storage. Storage bottlenecks are created when large amounts of data needs to be brought up to a relatively small amount of compute. In a processor-centric architecture, this involves moving the data across a bus up into the CPU, moving it into its memory subsystem, and then fetching it to actually do the compute that's required. If there's a large amount of generic compute that needs to take place, this architecture works very well. But if there's a very specific function, say an encryption, a compression, or even something a little bit more advanced like a database search or a regex filter, the amount of compute is relatively small, but huge amounts of data needs to be moved back and forth. And a general purpose processor is just not optimized for these type of workloads. By having a limited bus, you have high latency and limited bandwidth to the storage, especially as storage has become much faster with mainstream SSDs and now the emergence of storage class memory. Now the solution is similar. You move the processing to optimized hardware. So computational storage is a new architecture where you actually take the compute functions for these data-intensive tasks and you move them. And you have them take place directly next to the storage and sometimes within it. In this type of architecture, these well-defined functions are done with a dedicated hardware resource that is able to churn through the data much more quickly and only send a limited subset of results up to the CPU. This reduces the required bandwidth, it reduces latency, and ultimately it makes more CPU cycles available for generic processing that CPUs are quite good at. FPGAs provide optimized hardware while maintaining flexibility. And let's look at how that's done. If you're not familiar with FPGAs, they have a few advantages over other types of hardware. Ultimately, when you're trying to get performance, you have one of two paths that you can go down. One path is to optimize your software and adapt it to the hardware that's in front of you. What FPGAs do is they flip that on its head. Rather than having the algorithm mapped to the hardware, you actually have the hardware mapped to the algorithm. And you can implement a customized architecture so that each step of your algorithm happens in order directly from one function to the next without entering any intermediate steps, delays, latencies, or pipeline. This gives you the performance, power, and latency of dedicated hardware, but because of how those elements inside the FPGA can be reconnected, it gives you the reconfigurability of software. And this makes it much more economical than ASICs or ASSPs for many applications where there might be evolving algorithms or where there just may need to be different ways that you deploy it. So let's look down here below. This is an implementation of an FPGA where there is the input-output I/O on the outside of the chip, and internally all of these different elements that can be connected in a way to implement a custom architecture. So for instance, we can implement an encryption accelerator, and we can have high performance network packets coming in that need to be encrypted before they're sent on to the host, or decrypted, for instance, when they need to go back through the other path. And because the FPGA is reprogrammable, you're able to actually load up a different hardware architecture that can use all of the resources either for encryption or decryption using the same device. But you can even do more exotic applications such as analytics, where you may have a lot of data that's flowing through it and you're trying to do a filter operation, a scan, or an aggregate. You can use the same device to take advantage of that custom hardware path. Now, the major disadvantage that most people have when it comes to FPGAs is there's not as many people that understand how to program them, and they tend to give you maybe a little bit too much of a blank canvas where you have to decide how the I/O is assigned, come up with an interface so it can talk to peripherals before you can really get to the actual algorithm development. So what Xilinx has actually done is recently we've released Vitus. And Vitus enables you to actually write an algorithm using an upper level language such as C and focus on the development of that algorithm without having to write the hardware interfaces and really focus on how that actually gets synthesized. And as part of that, we've been developing different platforms that enable you to focus on different types of acceleration. And I want to go into what a couple of those are. The first platform that we're going to look at is a networking platform, the Alveo U25 Smartnic. This was recently released and incorporates some technology from SolarFlare, who Xilinx recently acquired. The way that this works is that the host actually just sees a standard NIC. It just runs the standard networking drivers and uses it to interface with the outside world. But rather than going straight to the outside world, there's an FPGA where bump in the wire acceleration kernels can actually be implemented. So for example, the earlier setup where we're looking at virtualization offload of the virtual switching, that can actually be implemented in that FPGA to offload that work from the host and have virtual network interfaces that are presented afterwards to the hypervisor. We're also enabling this to have Vitus platform support, and the FPGA is directly available via second PCIe port that can be used for offloading functions like ML inference and so on using that Vitus platform. This platform approach enables rapid development of acceleration without having to develop all of these interfaces that would be needed if you had taken a traditional FPGA design approach. But you can see here this is clearly a networking targeted platform, and it's not the only one that Xilinx has developed. So we'll take a look now at a storage platform that we've developed with Samsung. This is the Smart SSD. And inside of this Smart SSD, there's both an SSD controller and a Xilinx FPGA and direct access back and forth between the two outside of the access to the host. So there's large internal bandwidth, so data doesn't have to move outside of the SSD. This is great for when you need to process large amounts of data. When you're doing something like data format conversion, filtering, where you're looking for a particular value, even metadata management or analytics, all benefit from this tight integration between the compute and the storage. Other types of applications can also benefit. Things like video processing, where you need to do the conversion of one file format to another, and you can't start until all of that data has been uploaded, is well suited for having this compute near storage approach. And even some AI applications, such as tagging files as they're uploaded for later search and retrieval, is great for this type of architecture. There are two other benefits that you get from having this tight integration between the accelerator inside of a standard SSD product. The first one is that it opens up deployments where adding an accelerator might not have been possible before, such as in an edge deployment. A lot of data is created at the edge, be it video, be it Internet of Things type of data, and having the processing right next to where the data is stored in those deployments makes a lot of sense, and using the standard form factor really enables it. The second area is if you have an application where the amount of processing required scales with the amount of data. A lot of analytics kind of fits this template. So let's take a look at an example. In this case, we're looking at a setup where some ad hoc queries need to be run against a Spark database. Now, there are some solutions that have been written for the Smart SSD where the query processing is sped up when it's implemented on the FPGA. The FPGA is quite good at doing things like a scan, where it's looking for a value, a filter, where it's getting rid of values that don't match, and then aggregation, where it's counting the numbers that meet that data set. So in this case, we're looking at an airline traffic data in the US with 1.2 billion entries on flight data and another 1.2 billion entries on airports and planes. And then some typical ad hoc queries that are being run against it of trying to see which of the cities have the most delays and which one has the worst record. What happens with this deployment with the Smart SSD is you're able to actually scale up that ability to do that analytics processing with the number that is installed, so you don't get any slowdown as more and more data is entered. So for this setup, where there is no accelerators versus one, you can run about 4 times faster. However, if you spread the data set across more of these drives, you end up getting a doubling of performance and then quadrupling roughly when you have about 4 of them. And this way, you're able to get more performance as you have more data. Now that we've looked at both the storage and networking platforms that are available for targeting acceleration and bringing targeted workloads onto optimized hardware, let's think about where this is going. So the future directions have a lot of accelerators in solving some data center challenges. When we look today, current data centers are often designed with a standard server type. Each of these has fixed resources. There's a certain amount of storage, a certain amount of general purpose compute, and a certain amount of acceleration resources, and then networking that allows different workloads to communicate with one another. What people really would like is to be able to have pools of resources, pools of general purpose compute, pools of storage, and pools of accelerators to basically target exactly what's needed for a workload. And why isn't that done today? When you look at this, if you're carving this up, all of that traffic that used to be local within the server now gets spread across a network and increases the latency and really challenges the bandwidth. So even though networking has gotten quite a bit faster and is going to continue to get driven forward, it's still a major bottleneck that holds back being able to provision exactly the amount of resources that workloads actually need. So how do we solve that? Earlier, whenever we encountered situations where there was reduced bandwidth and high latency, we added some acceleration right next to where it needed to be. And that's really how you solve this problem. Let's look at a server of the future. So right now, we can have a server that has an accelerator that's plugged in that shows up as a physical function that enables you to offload the CPU for targeted workloads like ML, like video processing, and so on. What we can do is we can actually add this network connectivity and have a network acceleration kernel that happens as a bump in the wire. And to enable that, all that has to happen is another physical function gets presented from the same device across the PCIe bus that is able to encapsulate those network acceleration without actually having the CPU even be aware. But the next thing that makes sense to do, since we have this external network connection, is to look at moving the storage out of the server into a centralized pooled resource. And at this point, you're able to actually just present that remote storage, which may have a large number of storage features. It may be a virtual volume, it may have data protection, and so on. All of that can be handled via an accelerated kernel that is hidden within that Smartnic, and then is just presented as a standard NVMe physical function. So at this point, we have an accelerator that is presenting a compute acceleration, a standard block storage device, and a standard network interface that is hiding some of these low latency, high throughput functions right within that accelerator. However, we don't need to stop there because we have moved some of the resources out across the network and they end up having high latency as well. So the solution is actually looking at adding accelerators on both sides of the wire. So once we add in a remote SmartNIC next to storage, we can solve some of the problems that would come with moving those resources out of it. So once you have the accelerator also close to the storage, you're able to both present that remote virtual storage, you can accelerate functions right next to the storage, and also there's no need to have the accelerator that's in the server be as large as it might be otherwise. In many workloads, it's possible to have that accelerator be remote as well and just handle the presentation of that accelerator as if it was local, even if it's out over across a network. And this hyper-converged architecture enables you to solve a lot of these latency and bandwidth challenges. So when we look at this, when it all comes together, we have the future data center with this distributed adaptive acceleration. There's reduced network traffic because there's small amounts of acceleration each spot that it's needed, whether it's by storage, whether it's within the server network stack, or if it is in pools of accelerators. And this way you're able to actually optimize the workload, optimize the data center utilization. If you have something that needs 9 accelerators and a certain amount of storage, certain amount of general purpose compute, you're able to just provision that. And the secret is basically adding that accelerator into each piece of it. So you can carve it up exactly how it's needed to have a workload, whether it's small or very large. All of that can be put together very easily and with that reduced network traffic because the acceleration is handled where it needs to happen. So this new era of software-defined hardware infrastructure, it's really starting now. We went over the Alveo Smartnics that enable hardware optimization of networking, and it's a platform approach, so it's actually programmable and targets a new area of software developers. We also looked at computational storage and how that removes these storage bottlenecks with that same programmable platform approach. And we really feel that Xilinx is leading the way and is an enabling technology to enable this future of distributed adaptive acceleration. I appreciate your time, and I hope that we'll have a chance to meet in person at some point in the future. Thank you. Well, great. Thanks for joining this presentation. I'm actually live now, and there's a Q&A panel. So as the questions come in, I'll go ahead and answer them and just repeat them here for everyone to hear. All right, so we have one question that's on the line, and it's asking about how the Xilinx and Samsung solution differs from what other vendors are providing within the computational storage area. And in many ways, I would say there's a lot of similarities. And there's a goal towards being able to standardize computational storage and have it be provided from a number of vendors. So SNIA is very actively involved in that area. There's a number of approaches that people are taking, and it's a little bit more of a standardization movement to make sure that there isn't just a single bespoke provider, and I encourage you to take a look at that. All right, so another one in the air traffic demo, is that a provider from Bigstream or is that from somebody else? And so Bigstream is the partner that has provided a solution that allows for abstract query acceleration to be implemented within Spark. So that particular demo that we're looking at, or that example, I guess, that was looking at the Bigstream solution. We do have other partners that have developed solutions as well that can do various other types of implementations with different database front ends. But we do like the approach that has been taken where we've created a basic platform. We've released some libraries that allow our partners to create solutions, and then they're able to do the customization towards a particular kind of runtime environment and so on. Okay, another question, and it is there already a management tooling set available to leverage the technology? And so the answer to that is yes. We've been working at Xilinx towards developing a developer environment for quite some time, and have developed platforms as part of a long-run strategy that we've had for some time. And so that Vitus tool that we mentioned, that actually has everything that's needed from a developer's perspective to create those custom functions. But the same part of it is that we've open sourced the drivers that are needed to talk to the accelerator. And a lot of this platform approach has been to use those standard interfaces. And so the standard management techniques that you would already use kind of apply. For the networking platform, you end up using the same network management interfaces. And in some cases, the solutions that you'd run on top of that, they're kind of basically just completely turnkey. You just deploy it and it runs. Similar setup with storage. Like with the earlier question, we have a partner that just plugs in exactly into the Spark framework. All right, another question. So how do you ensure seamless software programmability across all the places where these accelerators are located? So that's an interesting question. And basically, the Xilinx has worked towards having adaptable programming of our devices for many, many, many years, and decades, in fact, right? And so that type of software programming, or really hardware programming as well, has been in place for quite some time. The key to being able to deploy different devices, though, is really to standardize the interface. And that's where there's a few interface standards that have been developed at the networking layer, at the storage layer, and even within the hardware layer for just kind of streaming and memory mapped interfaces. And that's a big piece of how we are able to ensure that you can deploy all of that. So another question, it says, later, do you see integration of network connections directly into disaggregated external smart storage controllers, or keeping a separate accelerator NIC talking to the disaggregated drives?
And that's an interesting question that we have across. The short answer is I don't think that we're sure. And one of the areas that we've looked at is that for some workloads, the co-location of the acceleration within the media device directly enables this higher bandwidth and this tighter coupling, and you can ultimately do some things that you can't otherwise. Like if you want to integrate some of the flash management or new media management within the acceleration, you really have to do that within the device for that to happen. And it's perfect because it's an adaptable device. There are other efforts underway to also have those storage devices to be able to talk directly to networks rather than having to go to an intermediate bridge. So I do think that that will continue to develop. But I do think as well there'll be other cases where being able to have modular replacements is also going to be a question. And there'll be the desire to have a larger centralized accelerator in front of it of a number of devices. And as far as today goes, that's the only way that really the interfaces are completely well-defined for that remote case. So I'd say in the near term, that's what will happen. And in the fullness of time, I think there'll be a number of approaches that are used. One more question. So let's see. So if someone wants to be able to deploy these, do they go directly to Xilinx or to a server vendor that works with Xilinx? So there's a number of ways that people can deploy. We have had partner OEMs that are providing our solutions as part of fully qualified releases. So for example, the Alveo U25, which is a compute accelerator, is available through Dell. And there is a number of other partners that have released this as well, I believe Inspur and so on. And so that's a big part of making sure that you have the server infrastructure connected to the accelerators in the correct way. So a lot of BMC integration and so on. So in many cases, you will actually go to that server vendor, but that's a continually evolving space. And so in some cases with these new technologies, they haven't been released via an OEM server just yet. And in those cases, you work with Xilinx directly. And the second part of that question is whether or not we were looking to partner with additional server vendors. And the answer to that is yes. We are looking at this as a way to fully deploy, provision, and have adaptable acceleration deployed, and are working with a number of server vendors. All right, well, I think we've gotten all the questions that came across, and we're about out of time. So I really do appreciate everyone staying till the end here with this new virtual presentation environment. And I hope that we have the chance to meet again in person soon. Thanks so much.